you've got 3 units that come off of 1 condenser. What happened was, while taking the panel off of this box, we shorted one of the legs. So when you check the legs coming in, you're supposed to have 208 volts between the 2 legs, but we only have 120. So that was my first clue. I checked the boards, and the boards were all good. But yeah, we didn't have the correct voltage coming in. So then I started tracing it backwards. I checked this switch. The switch was good. And I also noticed that on the same breaker, we had several other units. 3 units, right? So you turn the breaker on, and you get power on the other unit. This one here, right? And the other one in the other room. So you know that it's somewhere between that unit and that unit, right? It's not the breaker. You don't have like one breaker tripped. So then I start tracing the wire back, and I figure out that it goes outside. So you go out to the condenser. And the condenser has a spot where all 3 units plug in. So this is it's like a Fujitsu or something. Fujitsu VRV mini split type of thing. So all of the indoor units come and plug in, and they actually get their power from the outdoor unit. And I checked everything here, and everything looked good. I had, between red and black, I had 208 for unit A, for unit B, and for unit C. So then I noticed, wait a minute, what the heck are all these crazy looking things? These are fuses. These are little fuse holders. And I actually did notice a difference, I think, on this unit with my meter. And so I started here, and as a matter of fact, the very first one that I checked, this one had no continuity on the fuse. Yeah, so you pull that apart, there's a fuse in there, check continuity, bad fuse. So I got to get myself another 5 amp fuse. Anyway, so that should power that indoor unit back up. So it's a silly mistake, but luckily it's just going to be a fuse. Okay, so let's look at a 208 power supply and what you're going to see when you check it with your meter. So here we have the neutral on top is white, the leg 2 is red in the middle, and leg 1 is black on the bottom. So leg 1 and leg 2 are hot, and the neutral is not. Now, when you put your meter between, you put it on to measure volts, and you put it between black and white, so between leg 1 and neutral, it's going to read 120 volts. If you put it between leg 2 and neutral, it's going to read 120 volts. But why, when you put it between leg 1 and leg 2, do you read 208? If each of the legs carries 120 volts, why would they not add together to 240 volts? Why only 208? So let's look at the way that works. So here is a transformer. This is a single phase transformer. So on the left, there's a coil on the left. That's the primary coil. The coil on the right is a secondary coil. You've got a neutral tap in the middle, directly right in the middle of the windings of the secondary coil. So a transformer is 2 coils of wire near to one another. The primary side carries a current, and through electromagnetic induction, that current is induced onto the secondary winding, the secondary coil. The number of turns in the secondary coil determines the voltage output. So let's just imagine that these 4 turns are going to produce 240 volts. So the windings are also called the phase. So we have one phase here. And that winding is capable of producing 240 volts. So if you were to take your meter and put the red lead on L1 and the black lead on L2, it would measure 240 volts. But if you put your lead on neutral, one lead on L1, one lead on neutral, you're going to read 120 volts because that's half the coil. You've got half the number of windings capable of producing power or voltage. And the same between neutral and L2, 120 volts. So let's look at the sine wave that each of these two legs would produce. So if you measure between L1 and neutral, you'll get a sine wave like this if you use an oscilloscope. If you measure between L2 and neutral, same thing, 120 volt, and the sine wave will look like this. And they are happening in the same moment in time. So they're overlapped, basically. And so we can, because they're happening in the same moment in time, we can add the amplitude together. So the amplitude is the distance between the midline and the crest. So it's just how big is the wave. So if each wave, if each of these legs is producing 120 volts and they're happening at the same point in time, you can add them together, 240 volts. So where the 208 is different is the generation. Like, where does it come from? It comes from a different looking transformer. It comes from a three-phase transformer. And the phases are 120 degrees out from one another. So let's see what that looks like. So here we have a three-phase transformer. You can tell it's three-phase because it has 3 windings. So the winding is also called the phase. So each one of these phases is capable of producing 120 volts. I should have written L3, leg 3, down there on that last one. But you also have the neutral tapped in the middle and the ground. The neutral is also often grounded. So if you measure between leg 3 and neutral, you're going to get 120 volts. If you measure between any of the legs and neutral, you're going to get 120 volts because each of those legs, each of those phases, is capable of producing 120 volts. So you're measuring that coil alone, right? So the neutral taps in right in the middle, and so it's as if you're just putting your meter leads across that one phase. But what if you put your meter leads across 2 phases? What if you put it on leg 1 and leg 2? You're going to get 208 volts. Well, why not 240? It's 208 because the phases are not producing the power in the same moment in time. So the waves do not line up perfectly, and this is what it looks like. So you have 2 sine waves, but they're not happening at the same time. So each sine wave is the same amplitude as the ones from the single phase transformer, but they're not happening at the same time. And so you can't add them together. You have to add where they intersect. So the amplitude where they intersect is smaller, so the power is less, or the voltage is less. So that's what it looks like. And that's why 120 plus 120 sometimes equals 208. So it's important to check between the legs, because if you have a blown fuse on one of your legs, so one of your legs is not producing 120, if you check between leg 1 and neutral, you'll get 120 volts. And if you check between leg 2 and neutral, you'll get 120 volts. And that's because, even though leg 2 probably has a blown fuse, that's because 120 volts from leg 1 is going into the device. Like, let's say the fan motor has some windings in it. If it's a 208 volt fan motor, the windings in that motor are connected together. So 120 volts from leg 1 goes into the fan motor and comes back out on the other winding, which is connected to leg 2. So when you read leg 1 to neutral, you're reading the origin of the power. So the leg 1 is good. And when you read leg 2 to neutral, you're really, again, reading leg 1 to neutral. So you have to check between the 2 legs and be sure that you get 208 rather than just, well, actually, I think it would read basically 0. If you measure between the 2 legs, you're not going to get 208. You're going to get something very low, because you're essentially reading the same leg twice. Now, when it goes through the windings of the motor, the current or the voltage can be affected. So you might not read 0, but you're not going to read 208. So if you don't get 208 when you're supposed to have it, that's a red flag. You've probably got a tripped breaker. Like if the breakers are, if the legs are separate on different breakers, you might have a tripped breaker. Or if you've got fuses on the legs, then you need to go check your fuses because you've lost a leg somehow.